Professor Craig David Thompson. For you students, you should know that he is an alum of Western Wyoming Community College. He's been a professor of engineering and earth science at Western Wyoming Community College since 1991, and now I understand you're Professor Emeritus. Is that correct? I think that means he's retired, but he seems to be quite active anyway. He also has served and maybe continues to serve as University of Wyoming Adjunct Associate Professor in our College of Engineering and Applied Sciences. From 2009 to 2012, Professor Thompson served as a visiting scientist and sabbatical guest at the Department of Aquatic Ecology at the Swiss Federal Institute of Aquatic Science and Technology. And I think he'll tell you something about that. He's also a licensed professional engineer. As I said, Professor Thompson received his Associate of Arts degree in chemistry here at Western Wyoming Community College. He completed his Bachelor's of Arts degree in chemistry at Colorado College and his Master of Science degree in Civil and Environmental Engineering at Stanford University. Prior to his work here, coming to Western Wyoming Community College, he was the director of a U.S. Environmental Quality Protection, EPA, Certified Water Quality Laboratory for a number of years. And from looking at Professor Thompson's CV, you can tell that he has been quite successful in all his endeavors. He's been recognized with a number of awards for teaching, and he has received a number of grants from the NSF, NASA, and he's the author of a number of publications. So his little bit of information about himself is, I think this is pretty darn interesting. I'm interested in cars, but apparently Professor Thompson restores old motorcycles to reduce stress. So today we have the opportunity to learn from his expertise in his presentation entitled Climate Change in the Alpine Zone. So please help me welcome Craig Thompson.
Water, the God molecule, I call it. That's what unites all living systems, and it is what unites our presentations today. I included this slide on the cover of my presentation to show you an incredible ice formation on that little cobble in the center of this photograph. Not sure why this happened, and so I called up one of the University of Wyoming's Nobel Prize winners, Gabor Vali, and I said, please explain this to me, and he said, I can't. I tried to get another view of that, and as soon as I had moved, that little feature collapsed. And I think it is an indicator of the fragility not only of ice in the Alpine zone, but of the Alpine zone itself, perhaps an early indicator. So what I'm going to do is talk about climate change. Let me begin by defining the Alpine zone. This is not something that we've talked about today. This is the best guide that I know of. This is a book by Ann Svinger called Land Above the Trees, and it's a guide to American alpine tundra. And I'll probably be referring to this a little bit later on. But it is the mountainous region above the tree line. It's characterized by the fact that we have persistent snow and ice in this area throughout the summers. It occurs at almost any latitude, but usually high in elevation, and as we approach the poles, the elevation drops, and I'll talk about that a little bit later on. But the Alpine zone is inhabited by very specialized plants and animals. And this is an ecosystem that is under great stress. Here you can see a remnant ice feature of a glacier that you can barely see here. This is on Mount Kilimanjaro. I'm not exactly sure what the latitude of that is, but it's fairly close to the equator. This is a map showing the ice cover in, or a profile drawing showing the ice cover in 1912, and then you can see what has happened by 2002, and this is a 2012 photograph, so you can see that we just have this bare ice cap left. This is the Matterhorn. This is not a glaciated region. Although the region has glaciers, the Matterhorn itself does not have glaciers. And just in case you didn't think we had a Matterhorn in Wyoming, you can see this little feature which is in the Dinwoody region in the Cirque. Amazing, in its similarity here, but this thing was only about this tall. I show here a Piedmont glacier. This Piedmont glacier is in Argentina, and this thing is melting so fast, and the substrate here is so large that no meltwater streams exist. Now, one of the things I forgot to tell you last night, if you were here, was that I'll be talking a lot about ice and the importance of ice, and trying to reduce some pretty complex science into some lay terminology that hopefully will give you an appreciation of the importance of these areas. Okay, so let's talk about why glaciers and snowfields matter. They are the key to alpine ecosystems. I call them the alpine zone's thermostat, and I have an explanation for that. Glaciers and snowfields delay runoff to when we need it later in the year. When we have surplus snow, they turn that snow into ice, and they also are responsible for producing an aquatic ecosystem right at the toe of the glacier. And they provide habitat. They provide habitat for important animals, and I'll be talking a little bit more about that later on. What are the animals? Well, most of you have probably read about the pika, a rodent that lives above tree line. This is, are there any entomologists in our, good, then I can call these things what I believe they are. This is the Lednia tumana, the glacial meltwater stonefly, first identified in Glacier National Park. And this is an ice crawler. Dr. Clark's husband, another Dr. Clark here at the college, was my entomology professor. And he talked to me and told me about these ice crawlers that when you capture them, they will die in your hand because they are so acclimated to living at freezing, at the freezing point. So here are a couple of animals. These are the Chironomids diamensa. These are black fly larvae that live in aquatic ecosystems, and this is a mayfly that I'll talk about. One of our students is doing some research on this mayfly. This is also an amazingly hardy animal. We collected some of these in the Window Range, sent them to Switzerland. We had them at minus 20 degrees centigrade for 6 months. Warmed them up to identify them to see if these were the same chironomids that we had found in Switzerland. And after 6 months at minus 20 degrees, at least one of them started living again. So these are amazingly adapted animals to the alpine environment. Okay, let me see if I can put this into some perspective for you. I'll be talking a lot about ice. I want to give you some headlines out of the Rocket Miner, April the 1st of this year. Antarctic ice may melt faster than expected, and they refer to a scientific study. A forecast for extreme heat, they refer to another scientific study by meteorologists. And this is just from a couple of days ago, April the 16th. The Greenland ice sheet melts freakishly early. El Nino is weakening, and here comes La Nina. Scientists blame El Nino and warm temperatures for a gruesome coral death. Folks, this is stuff that's happening right in front of us right now. It can't be a more relevant topic, in my opinion, to what's going on. Now, in some of the preliminary stuff and some of the preliminary publicity that was put out about this event, we talked about my presentation, and in particular, we talked about the range and fluctuations. At higher latitudes and at higher altitudes, we're going to see greater changes than we see in lower latitudes and lower altitudes. In the equator, for a mean temperature of 2 degrees, global mean temperature that JJ pointed out, we'll probably only see a single degree of temperature increase at the equator, but we're going to see 4 degrees increase in the alpine zones and in the polar regions, okay? Now, you might ask the question, why do we study aquatic ecosystems? Because they have definite boundaries, they're accessible, and they're the smallest distinct alpine ecosystems, and for lazy people like myself, they're an ideal environment because we don't have to do mass surveys over broad landscapes. We can just follow the streams to their source. Why would we expect greater temperature changes at higher altitudes and at higher latitudes? Well, as the diagram that JJ put up indicates, alpine zones basically are heat reflectors, all right? And they're reflectors in proportion to the snow-covered land area. Look at the amount of snow and ice cover in this photograph and contrast that with the amount of snow and ice in this photograph, and then with the snow and ice in this photograph. These are not all alpine zones. Mary will bust me, Mark will bust me saying, hey, that's Aspen Mountain, but I needed an illustrative photograph, and so I ran out there the other night. So we're not going to get as much reflection here as we get here, and even less in this area, okay? And so traditionally, those parts of the planet that have been great heat reflectors are now turning into heat absorbers, and so they become proportionately an area that will be subject to greater climate change. Clear on that? Does that make sense? Okay. So we began our studies in the Wind River Range in 1983, and JJ's work is right up in here. The Wind River Range glaciers in the beginning part of the 1900s were thought to contain 125 glaciers, which the United States Geological Survey mapped when they first mapped this area. 23 of these are named, and they have an extent which is roughly 50 miles in length. They are the most abundant of all glaciated areas in the contiguous United States. Okay, we have more glaciers in Wyoming than in Glacier National Park and the Pacific Northwest combined. Few people realize this. So we began our studies actually by looking at acid rain. We were interested when we had a water quality lab here in the chemistry of the precipitation, and we began by looking at the Wind River Range glaciers as reservoirs, as textbooks that we could thumb back through time, and by coring, look back through time to determine the chemistry of the atmosphere when those snow particles fell to the glacier and then were mashed down into ice by the subsequent snows, okay? And what we found was that these glaciers were enriched in copper and in zinc and in lead in a trajectory that was mappable from the copper smelters of southern Arizona, okay? But this was almost insignificant into what we as researchers find when we look at something new and realize that that was important, that was cool, but what was really cool was we discovered an extinct species of Rocky Mountain locusts, okay? So if you look at the insect parts here you see a full body, here's a tibia, there's some fibula, there's some wings here. What we found when we went in to determine the chemistry of this glacier was we found lenses of grasshoppers which were captured in those glaciers, okay? We didn't know anything other than to take a sample and to get a hold of somebody who knew a lot more about insects than we did. And so we called an insect scientist, an entomologist from the University of Wyoming named Jeff Lockwood. Sure, send him down. He was used to weird fellows like us coming to him with strange questions, and we sent him down. And he called me back a few weeks later at 11 o'clock at night and said, "You're not going to believe this, but in the sample you sent me, these insects were all of the same sex, female. They were all the same insect, Melanopus spretus, and that insect went extinct almost 100 years ago." And in subsequent research that Jeff did in writing this book, Locust, which is a great read, by the way. He is a gifted writer, and if I could step aside here and say anecdotally, the University of Wyoming, they're light on their feet and they can move, and I appreciate this quality. He is now in the Department of Philosophy and Creative Writing. So an entomologist that actually was able to cross disciplines like that. And I think that is great testimony to the University of Wyoming that they build upon those strengths. In this book, he details why this insect went extinct. This insect was once the most numerous of all individuals on the planet. In the early 1900s, the locust plagues that infested the central plains of the United States were this very species, and this species is now extinct. And so I include here a little quote by my favorite scientist at this time, E.O. Wilson, that says it's the little things that run the world. And when habitat destruction, which is what was essentially responsible for the extinction of this species, of the most numerous of individuals on this planet, the greatest population, it should really give us pause to consider our own fate on the planet. This is a quick photograph of Knife Point Glacier. And this is Jeff Lockwood. This guy is Wolfgang Baer. He's a filmmaker. He produced a film that was, he is an Austrian. It was produced in Germany, and it was called Glacier unserer Welt, and was shown once or twice here in the United States, but was never. But he was fascinated with this whole thing, and this all of Jeff's research ended up in being published in this book, which I would recommend to you highly. So this is where we started. 1984 was our first expedition, and we're still doing work there. I have been accused of, maliciously accused, of taking an academic junket to Switzerland, when in fact Switzerland has several things in common with the state of Wyoming. When I told people that I was going to go on sabbatical leave in Switzerland, eyebrows were raised. Oh yeah, Switzerland, huh? But it turns out the Swiss people care about their glaciers a great deal. the glaciers are very, very important to them, and they're out there all the time. They have Swiss glacier monitoring services. They know exactly what's going on with all of the glaciers all of the time. And I teamed up with, through Jeff, with more biologists, because it turns out that our work in the Wind River Range not only indicated that our glaciers were melting catastrophically, the geological and geographical importance of which cannot be understated, but the biology turns out to be very, very important too. And so I switched from working with chemists and geologists to working with biologists and looking at the ecosystems that are present in these alpine areas, particularly in the regions right around the glaciers themselves. So these are the glaciers that we're studying. They're all sort of in southeastern Switzerland, east of the Matterhorn. And these are the years that we have studied, and that's the purpose. The link between Switzerland and Wyoming is not population. This is Wyoming. There are more people in Zurich and its environment than in our entire state, okay? And this is the size of Switzerland shown relative to the size of Wyoming. It would fit almost entirely within Sweetwater County, okay? It's a very small country, a very populous country, so that certainly can't be the link there. That can't be why I can explain my sabbatical to anyone. But the glaciated region is very important. At one point, all of the gray area here was glaciated in Switzerland. Now just the white areas are glaciated. And this is the steady glacier that I'm going to come back to over and over again, although we actually have 8 separate steady glaciers in Switzerland. Here's something real interesting. 42 degrees north latitude, the state of Wyoming. You can see here outlined in blue our glacier fields. And here is Switzerland. And if we adjust the geographic scale to match, then move the country in, you can see that it is roughly in area and in length equivalent, okay? But that's not the most important thing. Our glaciers are all higher, okay? Their glaciers are 46 degrees to 47 degrees north latitude, and ours are lower in latitude but higher in elevation. Look at Morteratsch, for example, roughly 7,000 feet. We don't have any glaciers that begin at that elevation, okay? Here's why it's critical. Look at the runoff here. Wyoming is the headwaters of the western United States, okay? Here is JJ's study area right up in here, okay? The Wind River Range Glacier Field, headwaters of the Snake and the Columbia, the headwaters of the Wind River, the Yellowstone, the Missouri, the Mississippi, the headwaters, I keep pushing the wrong button. The headwaters of the Colorado and through the Green River, okay? And in Switzerland, we see almost identically the headwaters of the Rhine River, okay, through the Inn River, and here's where our steady glacier Morteratsch is, through the Danube and into the Black Sea, and then the Po into the Mediterranean, as well as the Rhone River into the Mediterranean. This is a slide that JJ showed you earlier. Here is one of the reasons I studied in Switzerland. They make serious research efforts to understand their country. 1% of all of Switzerland every year is studied intensely in terms of the geology, the biology, the chemistry, and the ecology. 1% is set aside, and there is a report written and sent to Swiss citizens or made available to Swiss citizens. And when I see in the Wind River Range people in top coats and in dresses appreciating their glaciers like the Swiss do, then I know that my mission will be complete and I can retire. Let me give you an idea of this catastrophic meltback that I mentioned earlier. This is an article from 1923. If you were to be in Pinedale, Wyoming, and look out onto the horizon, the highest peak you would see is Fremont Peak. The lowest point on the horizon, we're looking east, is Indian Pass. And this is Indian Pass. This is the flank of Jackson Peak, Indian Pass, and this is called the Elephant's Head or Harrower Peak. And this is a photograph in 1923. This is the same photograph, same location. There's Harrower Peak and the Elephant's Head in 1988. Where has all the ice gone? Same setting, okay? This is Indian Pass. This is zooming back a little bit. This is Knife Point Glacier here, Bull Lake Creek Glacier here. This is Fremont Glacier. And this is the same scene in 1988, okay? So our studies were basically on the leeward side, on Dinwiddie Glacier and Gannett Glacier. One of the reasons why these glaciers are not in public eye so much is because they are so remote, okay? But just because they're remote, it doesn't mean that they're not important. So we contrast this with Switzerland. This is Morteratsch in 1964. This is Morteratsch in 2011. This gives you an idea of the melt back in length. Now I want to make a very important point here, in that in the popular press, you will often see someone, I'm a professor emeritus, like Rush Limbaugh, I can say things like this, saying, well, we've got some glaciers that are advancing. And therefore, this global warming thing is just a fiction put out by scientists to increase their research grants, okay? That is simply not true, okay? What really counts is not the fact that some glaciers may advance, because if they're advancing and they're thinning simultaneously, or if they're advancing so fast that because they're melting so fast and they're now floating on rocks that they used to grind against, it doesn't mean that what's going on here is unimportant, and it is not a contradiction to global warming and the changes that we see. We are losing ice in the Wind River Range in terms of linear feet in meltback, 50 to 100 feet per year in many of the glaciers. That's huge, okay? But in Switzerland, they're losing it at 50 to 100 meters, 150 meters, 200 meters. I'll show you some photographs. This is an indication of some of this. Look at this so this is the source area, okay? This is Morteratsch Glacier in 1876, accurately mapped. This is the same area, maybe right in here is now the terminus of this glacier, okay? This side glacier no longer makes it to the main glacier itself, okay? To give you a little bit more of an idea, this sign here says this is the point at which the toe of the glacier, they call it the tongue, actually existed in 1920. You can barely see the glacier in the background. Get even closer and it disappears, and look at the size of the trees. This is where the glacier was in 1940. This is where the glacier was in 1960. Now we can begin to see the glacier. In 1970, this was where it was in the summer of 2009, right here. And this sign says, what does that say, 1990? And this is where it was in 2000 and 2010, okay? And interestingly, I'm going to refer back to this. I want you to look at this rock buttress because this rock buttress plays a very important role in this glacier. Where has all the ice gone? Very important here. This is Mark Meyer out of the University of Colorado, and he works at a research institute there that escapes me right now. But I want to point two things out here. This guy, by the way, wrote his PhD thesis on Gannett Glacier, okay? And he is 85 years old. I think he wrote his thesis in 1954 or something like that. Look at the trend that we're losing ice. This is roughly linear, but look what happens after 1990. This to me looks like exponential curve down, okay, which is the exact opposite of the exponential curves up that JJ showed in her slides. We shouldn't be surprised at this. Temperatures are increasing, and they are increasing at an increasing rate, okay? And so we're going to be losing ice at the same rate as we see temperature increase. Where's it all gone? Few people realize this. The major mechanism of ice mass lost, and that's the important thing when it comes to glaciers. It's not the length, it's not the area, it's the ice mass. The major mechanism of ice mass lost in alpine glaciers is not through melting, it's through sublimation, okay? And so you'll see here, in terms of ice volume, okay, Antarctica, much more important than Greenland, and the other glaciers are almost insignificant in terms of their ice volume, okay? But in terms of precipitation, okay, you can see Antarctica playing a smaller and smaller role. And down here, the other glaciers, okay, through sublimation and through direct melting into the sea, are contributing a much more volume to the increase in sea level than Antarctica and Greenland. Okay? The greatest ice loss documented so far, the Larsen B ice shelf, actually, I think it was an area the size of Connecticut and Rhode Island combined, collapsed a few years ago, but that wouldn't increase the sea level at all because this ice was already floating. Okay? So if I had an ice cube in here and the ice cube was sticking above the surface, when this ice melts, it's not going to increase the water level, okay? And that's why the great ice masses, the polar ice cap in the northern hemisphere, in the Arctic, and much of the ice in the Antarctic do not contribute to sea level increases. This is one of JJ's research collaborators, Brian Shulman. This alpine climate business is much more important than just snow and ice, as much as I like to beat the snow and ice drum here. So he reported that Wyoming, in 24 of the 30 stations, are reporting an increase in the number of record warm years. And this is the important point that JJ made. These cold midwinter nights are critical. Okay, and we're seeing a decrease in the number of these. And anybody who's lived in Wyoming for, 3 or 4 decades know that the days that we used to have below zero weather are far outstripped by the days that we have now of really cold sub-zero weather, okay? Average Wyoming temperatures, 3 degrees Fahrenheit. Okay, that's 1.7 degrees centigrade. And this is an important conclusion from this paper. For every degree of temperature rise, we expect rainfall to decrease about 3 inches. That's significant, okay? One of the people that participated in our early studies was Dave Nast from the USGS. If you ever see him, ask him how he got his helicopter unstuck when he landed on Lower Fremont Glacier. But one of the things they did was they did some ice cores, okay? They landed a helicopter, and it froze into the ice, and they had a difficult time getting it out. But the conclusion here is that he has definitive data, okay, using the chemistry of the ice cores themselves, that there has been rapid air temperature increases locally. This is not something that we're extrapolating from weather stations around Wyoming, but locally on that glacier since 1960. Okay, water vapor, water liquid, and ice are the Earth's temperature buffer. Let me see if I can explain this as I go through the conclusions of our studies. First of all, the snow and ice cover is going to drive the long-term changes in local alpine temperatures and the evaporation rates and precipitation, okay? How does this work? How is it that the thermostat here in the alpine zone is snow and ice? Here I want to take you through sort of a complicated physical chemistry diagram and see if I can translate this into terms that we can all relate to. First of all, glaciers not only cool the alpine zone in the summer, but they warm it in the winter. This is difficult to understand. How can a glacier, which is below freezing, right? How can that warm the, well, just imagine this. We move a minus 30-degree air mass into the alpine area over a glacier that exists at 0. And thermodynamics says heat is going to go from the glacier into that ice, or into that air mass above it, right? So it's going to warm the air mass, but it also cools it in the summer, right? And that's not hard to explain. You move a warm air mass into a glaciated alpine zone, and the glacier absorbs that heat, okay? Now let's look at this diagram. Here's something really, really important. As we heat ice, so we're adding heat in this direction, and we're changing temperature, increasing in this direction. So as we heat ice, we increase its temperature. No mystery, okay? We get to the point, this is actually a little bit off, this should, we get to the point where ice begins to melt, okay? And we add all of this heat, 80 calories per gram, and we don't change the temperature of the ice at all. All we do is change the structure of the molecules. We break the crystalline bonds of ice, okay? And that means that this can exist with, a glacier can exist with tremendous capacity to absorb heat, okay? Because for every gram of ice that we've got now, we can absorb 80 grams of heat, and then as soon as we melt it into water, when we put in 1 more calorie, okay, of heat, it actually is going to start increasing in temperature by 1 degree. How am I doing? Does that make sense to you? Okay, it's a temperature buffer. And look what happens when we sublime it. Look what happens when it evaporates. For each gram here, we now can absorb 540 calories of heat, okay? So this means that we are heating, melting, heating, evaporating in this direction, okay? And this is going to occur in the summer. And then in this direction, we are condensing, and we are giving heat off, okay? As the glacier has the opportunity to pass the heat that it gained back into the alpine zone. And this means that if you have a small glacier in a very large catchment, you don't have a lot of buffering capacity. If you have a large glacier that fills the cirque, or the catchment where it's located, you've got a tremendous buffer for heat. Okay? How am I doing? Does this make sense? All right. So, temperature increases. They're going to be non-uniform because look at the difference in color. Look at the difference in what our heat absorber region, the Alpine zone, has in just these 3 photographs here. Okay? It's going to be non-uniform. And again, I explained, I hope, that glaciers mitigate the alpine temperature swings by heating and cooling. We now have some data, which one of Jackie Clancher's students, a research student just like yourself, recovered some temperature sensors for us in the Dinwiddie last year, and we've got some data that shows my favorite glacier of all time, because of its name, Heap Steep Glacier, a very small glacier and a very large catchment, has huge swings in temperature in that catchment. Okay? Right next door in the Dinwiddie Glacier, okay, a large glacier actually filling the catchment in which it sets, okay, we get very, very slight changes in temperature. That will have ecological consequences. Okay? Okay? Question? Nope. I'm in a hurry. Okay, here we go. These are the conclusions that JJ has already put on. Snow is going to melt faster with higher peak runoffs. That's conclusion number 4. The runoff peak will shift earlier in the spring. She had a great graphic showing how that's working. One of the things that I haven't explained is that as these glaciers push down the slope, they grind up rock. This rock is suspended in this stream. It's called glacial flour. It is rich in nutrients that provide the basis for our ecosystems in these areas. And so we have, right at the toe of these glaciers, right at the tongue of these glaciers, we have a vibrant alpine aquatic ecosystem that exists at the freezing point, at 0 degrees. Look at these animals. Again, this is the black fly larva chironomids, okay? This is a photograph of the net primary productivity in the stream a little bit downstream, and this is closer. If we have animals that are used to living in this environment, subject to this environment, there's going to be changes that will result. And the alpine food web, especially in the stream systems, is changing as these alpine, in the alpine zone as these glaciers retreat. Okay? We'll also see an increase in erosion in the alpine zone. Ice basically acts as a subsurface glue, sticking all the particles together. Okay? Remove the ice, you remove the glue, and so you will get more mass flow, more erosion. Okay? But the ice also has got a lot of weight and it's pushing down on these subglacial sediments and holding them together. Remove the glacier, and there's nothing that's forcing those sediments, because it's keeping those sediments from moving. Okay? So that is one of the conclusions that we come to. Here is that little rock buttress that I talked about earlier. This is melting out of Morteratsch Glacier in Switzerland. Look at this little feature right here. What caused this ice to melt? Well, it was reflection off of this boulder of heat into the ice right next door. Okay? So this points to us that when you have more rock debris exposed, you're going to get an increase in the rate of melt of these systems. Okay, what we don't know is what those systems are going to do. If we have this caddis fly, which can no longer follow a glacial meltwater stream because it passes over a cliff, or because the slope, engineers would call this a shear force, the slope promotes a shear force that doesn't allow that animal to hang on and make a living, we're going to lose that animal, okay? And that we can say with assurance. What we don't know is what the next phase is going to be if this animal in its terrestrial phase, so after it goes out of the water, sprouts rings. If this was responsible for pollinating certain alpine plants, then we're going to lose those too, okay? So there are going to be nasty ecological consequences. This is my conclusion. You don't want to live in a world without ice. Ice is our buffer, okay? And as pointed out in James Hansen's book, Storms of My Grandchildren, we are going to have, without these heat buffers, we're going to have more numerous storms. The storms are going to be more intense. Our droughts are going to last longer, okay? And this is my conclusion. I look at alpine glaciers as God-given, no cost, zero maintenance, fully automatic, high altitude, climate buffering water reservoirs that are both vandal and terrorist resistant. And we're asleep at the switch. Nobody's watching other than Jackie and her group. A few University of Wyoming researchers have been looking at this, but we don't have near the attention that needs to be paid to the glacier systems. All right, so now a word from our sponsors. Got 1 minute here. I want to show you something really cool about Switzerland. This is a smart car vending machine. On the way to the airport in Zurich, if you've got 12,000 francs on your credit card, you can go in and stick it into this machine. This revolves. See these cars in here? It revolves. You pick one out of your color. It revolves down. A little door opens up. 3 guys run out. They take it out, fill it up, shake your hand, and off you go. Okay? I thought America was technologically advanced, but Switzerland is pretty cool. This is an interesting little insect here. This is a wingless moth, which is acclimated to the Alpine zone in Switzerland. We don't know where it exists anyplace else. Most importantly, one of the take-home messages that I want to leave with you is that the Alpine zone, because of its remoteness, is very poorly studied. We know almost nothing about it, and we know almost nothing about the terrestrial ecology in these zones. And that is a tragedy, to lose something like this before we know what's going on. Am I alone in this thinking? I don't think so. Okay, here are our students. You'll see that there are several here from Western Wyoming Community College. This goes through, and here's our crew, happy to be out of the saddle. I will take questions now. Oh yeah, here's my questions. And a reminder to all of our students who will be doing outdoor research, wear sunscreen, otherwise you're going to end up looking like this guy. You don't want that. Okay, questions? Yes?
Is it possible to recreate some of what is going on? Could we paint white or put a giant Christo-like canvas up there to at least do some of the reflection?
That's a great idea. It's a good question, Shannon. It's a great idea. Like many of my ideas that I always think are absolutely unique, somebody already had that idea. And they stretched a bunch of plastic over one of the glaciers in Switzerland. And what they found was that there is a rate at which heat passes from the Earth's core up through all systems, planet-wide. And what they found was that the plastic captured that heat and accelerated the glacier rather than reflecting the solar gain. So it's a great idea, but so far the answer is no. I don't know that they've tried anything else other than plastic. But the Swiss are really keenly interested in this. There are Swiss glacier monitoring institutes at all their universities, and a huge proportion. One of the reasons I went over there to study was it was the best place in the world to study. And there is a huge proportion of their researchers which are looking at these questions alone. The Swiss national parks were not created like Yellowstone for the enjoyment of the people. Is that what that sign says for the,
Use and enjoyment.
pardon?
Use and enjoyment.
For the use and enjoyment of their national parks were created for the understanding of the ecosystem. And so you can't walk off the trail unless you're a researcher and you've got a researcher band. They're very interested in this sort of thing. Yeah.
So, could you talk a little bit about what Swiss policymakers have been pushing in light of the technical information coming in regarding the glaciers? I think you're saying they've been very progressive in terms of the generation of the technical research. How has that translated into the policy realm? Is any of that relevant to the state of Wyoming or the western United States?
Yes. It is relevant. Let me give you some ideas. We talked earlier with Mark about the public transportation systems, okay? In particular, we were talking about Salt Lake City and as a post-Olympic city, how those infrastructure improvements came to be. In Switzerland, it is a national right to have public transport available within 500 meters of your home. And so they're very aggressive. Here's something that I heard a public policy enforcer, this was a planner in the city of Zurich, say on television. It's not my job to make streets wider for more cars. It's my job to make public transportation more available and personal transportation more difficult. Can you imagine the consequences of somebody standing up in Denver or Los Angeles and saying, I want to narrow the freeways? But the net result of that, in terms of energy use, is a decrease in energy use. The smart car is manufactured in Switzerland. It's the Swiss taxation system is geared for the displacement of your car. You can't hardly afford, even in Switzerland, to drive a Corvette with a large American V8 engine, okay? Because your tax is not based on the age of the car like it is here, it's based on the displacement of the engine. So yeah, those are a couple of policy areas. Is that enough?
Curious, land use planning as well.
Yes, land use planning is a huge deal over there. It's like I say, they're inventorying every year. 1% of the total area of Switzerland gets inventoried, and then that results of that inventory are made available. And the Swiss are not a retiring people when it comes to criticizing their government. If something is going on, they expect the government to do something about it, and so they're doing things. Most importantly, I think, for us, for the academics, they are investing a tremendous amount in research. They want to know what's happening there. Yes, JJ.
Great, thank you very much. This was a really great talk. I really appreciate it. Can you give us a sense of how much time we have with these glaciers in the Wind River Range?
Dude, you see what happens when you tell people you're going to predict the future, and you really have to do it. So, 3 things constitute a glacier. You have to have snow changing to ice. You have to have a clear zone of snow accumulation and a clear zone at a lower elevation of melting, okay? You also have to have ice formed under pressure, all right? And so the USGS has added a 4th definition. It has to be 25 acres in size. The ice has to move, okay? So if the ice is not moving, even that photograph with Gannett Peak in there, it's just simply a snowfield. It has to meet all 4 of those areas. I think of the 125 glaciers that were originally surveyed by the USGS. If we go with their definition, we've probably got less than 20 left, okay? Of those, I think all but how about less than 10? All but 10 are going to disappear in the next 40 years, 50 years. And the rest, you know, I mean, it's like you said, the flywheel is spinning. There's not much we can do about CO2 that's already in our atmosphere that's holding the heat next to the Earth. So we're going to lose a lot of this. What is sad for me is that we're going to have unpredictable impacts in these alpine ecosystems. Yeah.
So is it a conception that we get a good snow year and the glaciers are going to come back? Is that?
No. We get a good snow year, and let's say we get a terrific snow year. Well, look at last year. Last year, 15 years. In the last 15 years, we've had 2 years of normal precipitation here in Sweetwater County. Last year, we had normal precipitation, and we had it at exactly the right time. So the range bloomed, everything looked great. People thought the drought was over, but there was no additional accumulation of the glaciers in the Wind River Range. Why? Because the precip fell as rain later in the year. Okay, so a great snow year, which we have not had in the last 15 years, well, maybe one was fairly close. A great snow year, say 150% of normal, will give us a little lens of ice. But that's going to be a couple of hundred years away from a water supply. Okay, does that make sense?
I want to thank you for your presentation.
Well,
Can we all thank Professor Thompson?